All right, so let's start introducing our next speaker, Shih-Chieh Hsu from University of Washington. He's going to talk about AI on the edge and decoding particles, brains, and cosmic collisions in real time. And yeah, please, I'll leave you the floor.
Okay. Right. Can everyone hear me well? Great. All right. Yeah. So I'm going to talk about the AI on the edge, and specifically I'll focus on the edge computing, right? So before I start, I just do a quick poll. Does anyone identify this picture? All right. So they help me to understand the composition of the audiences, and this is the moment when we present the Breakthrough Prize for Fundamental Physics in 2025 for the full experiment at the Large Hadron Collider at CERN to about the dedicated measurement of the Higgs boson properties, symmetry breaking mechanisms, strongly integrating particles, and matter-antimatter research studies. And this is also a very nice following of the 2024 Nobel Prize. And together with this experiment and also the physics Nobel, and I would say that this nicely summarizes how the AI had been really contribute to the fundamental science in physics areas. So if I just draw a quick timeline about the particle physics fundamental discovery, starting from 1995, when I was a bachelor science student, I was undergraduate in that year, and a lot of fascinating discovery has been made. So if I take a look about the development in computer science, it's very interesting. In each year that when we have a fundamental particle physics discovery, there were also amazing fundamental computer science and data science algorithms being discovered and revealed to the world. And several of these actually also contribute to how we analyze data in big data science. And these development actually accelerate the discovery because of the way we knew how to understand our data better. So if I just look at the timeline forward, this is where we are right now. And starting from 2022, when ChatGPT just make the first public version in January, this overwhelmingly that have 2 million subscription of this service in just less than 2 months. This is an amazing accomplishment in terms of the publication, how software can be generalized to a global-wise inference. And this is the record. And ChatGPT considered one of the revolutionary the package and algorithm accessible to the scientists. And we'll be curious about what will be the next discovery over here. Okay? So it has been coined that starting from 2012 when AlexNet showed up, that the neural network using GPU can achieve to the level of 10 years old kids in intelligence. So since then, I think we all sit here have think about how the next level of the AI algorithm can bring us through. All right. So we are not just talking about algorithm. Actually, the reason why algorithm can move forward is also because of the hardware technology. Without computing element, we cannot do efficient computing, or we cannot even do a computing. So, and this is a Moore's law. This is a factor 2 of the every 7 years of number of transistors in a unit area being increased. But if you look at the AI models, in particular transformer-based large language model, this is clearly go beyond the Moore's law. And Moore's law is how industry, in the semiconductor, they can build the electronics. So it's more than just the computing element, but we also hit the memory wall. You need memory to cache data to compute. So this is the current limitations, and every single semiconductor industry are thinking about how I can go beyond this scaling law, because with that, and it's practically able to help us to allow our need of algorithm catch up and to continue move forward. Therefore, we need to think about what's the trending in industry. And if you talk about the computing programming flexibility, CPU is definitely very flexible. Like we can program easily, and even using Python, we can do, or Julia, depending on the language you like. We can easily do programming, the tests we want to do. However, CPU is not the most efficient computing element. And the one that can be really efficient in every aspect, the power, the speed, is the ASICs. And there are hardware in between, GPU and FPGA. And we are talking about how we can utilize all different devices for appropriate use of the need of computing. In the industry, so almost every big IT companies, they are designing their own AI ASICs in order to really make the best use of the hardware to serve the computing software they are inventing, which are mostly based on the transformer and large language model. So how about the science that as a scientist we have? It's not easy for us can build ASICs. So we sort of have to follow what the trend in IT to develop our tools. But today I'm going to tell you two approaches that our research institute, A3D3, is pursuing to help us to utilize the FPGA and the GPU. So many of the talks in this workshop are talking about algorithms you want to design and how you can train this large language model, even foundation model, that you have large parameters to fit the science you need. However, once you train the big model, if you want to apply to experiment, you need to think about the inference. And in inference, you are thinking about different questions because quite often the hardware resource is limited. Therefore, you have to design a different approach in mindset when you try to deploy those software to the actual experiment use. And this will be the focus of my talk. And what I will do is I will use particle physics as a starting point, and then how we learn from the particle physics development apply to neuroscience and also the astrophysics. So I'm part of the member of ATLAS experiment, one of the large hadron collider experiment. And this experiment, together with CMS, are contributing to the discovery of Higgs boson back to 2012 and lead to the Nobel Prize in 2013. So I would like to use this video briefly illustrate the challenge of the big data in Large Hadron Collider. And we start with circulating protons in opposite directions in collision in the center of the detector. Then all those radiation particles, they are detected by complicate detector with a different function and purpose. We digitize those data, then collect those into the offline computing for analysis. However, the data volume is so high, and also not every single event we are interested in. Therefore, we have a hardware device to filter the events. We only trigger the event of the interest in order to downsize the data and allows analyze more efficiently, focus on this interesting science. And we collect data from all experiments, the 4 major ones, and send it to the data center at CERN is called Tier 0. In tier 0, we will pick out our data in the tape for long-term storage. And also, we distribute those data to the other tiers of the computing. There are a couple of tier 1 computing all over the world. Then we can use grid for big data analysis. So this is the data flow of the experiment. Now, let me just quickly pick a few moments which are critical for my talk. So first, after the collisions, is a 40 megahertz rate, and we downsize data to a 750 kilohertz rate. And this requires to complete the inference calculation in microsecond. Then we further downsize data to 7.5 kilohertz. At this moment, each event is about 7 megabytes. And here, the requirement is to finish the inference calculation in millisecond level. And after that, we can store data to offline for using the grid for data access and analysis. The whole data volume we talk about here are exabyte scale data set. All right? So this is a gigantic data. To efficiently analyze this data in this workflow, we have to utilize different type of hardware. In the collision, in order to reach to the nanosecond, you have to use ASICs. And we now use FPGAs for most of case when we do the first level of the triggering. For the high-level trigger, you can use a CPU, or now we start moving to the coprocessor to integrate GPU to this system. And for offline, you can explore different computing elements, heterogeneous computing, and you can use a combination of those to pursue the best computational calculations. So I can summarize this a challenge in another part like this. The x-axis here is the latency, the time required to compute each of the inference. The y-axis here is the streaming rate. So every second, how much data volume we analyze. The large hadron collider, here we talk about microsecond latency. The data volume is 10 to the 14 bytes per second. So if you downsize the data to the high-level trigger, then the second stage of the trigger, and the latency here is a millisecond order, and the streaming rate is an order magnitude smaller. So if you look at purple here, in order to achieve this millisecond level, you can use a CPU or GPU. And however, if you want to really get to the microsecond level, you have to use FPGA or ASIC. That's why we need to use two different types of hardware tiers. So how to get a sense about the challenge we are encountering? Let's compare to the major IT company, for example, Google. So this is Google. The latency is about second level. And look at their streaming rate. It's 2 orders of magnitude smaller than the Large Hadron Collider. Therefore, Large Hadron Collider is driving the data volume and also streaming rate beyond the industry standard. And this is a very, very difficult challenge. We are not alone. And if you look at the multi-dimensional astrophysics and also the neuroscience, we all reach to this big data challenge at the equivalent level. So we need smarter algorithms and develop together with AI scientists. And also, we need to work with hardware experts who really know how to accelerate those algorithms in order to achieve our goal. This is why we assembled together an institute called A3D3. This is primarily sponsored by the NSF. All right, so I'm going to share with you 2 different aspects. One is how do we solve the latency problem. The other is how we can solve the high throughput problems. Let's start with the low latency. You need to think about the design of algorithms and hardware together. In the algorithm, the modern scientific data we are dealing with need to deal with irregular data distribution, and also we have scarce or limited labels on the data. And we also need to think about the interpretability of the data. And for the hardware, we have to optimize to support AI algorithms in order to address the need of low latency and high throughput. And we need to also think about the power. This is the really precious resource we do worry. So the algorithms, the package we developed is called HLS4MLO, and the primary developers and maintainers are from the A3D3 Institute. And we have support multiple different type of AI algorithms, and this tool can be used to streamline the process for developer to easily deploy to the FPGAs or ASICs. So the package can decompose into 3 components. One, the scientists can focus on the AI model development, and we have a tool can convert Python code to the high-level synthesis language, which can be further compiled to the hardware language can be understood by FPGA using the commercial software. And because of these 3 tiers, we are able to collaborate with the AI scientists here and also the hardware expert here. So as one example, we use a transformer, which is really the baseline of the large language model. So we can identify the example data from the gravitational wave, large hadron collider, and also the neuroscience. And we use the common transformer architecture to solve the data problem and try to deploy it to the FPGA. And we are able to achieve microsecond level of the latency if the model size is about 3,000 to 10,000 parameters. And we also apply to the actual large hadron collider data. This is an example that we have autoencoder deployed to the level 1 trigger, has been taking data since 2024, and we start getting the scientific result with the 2 algorithms. And here is one example show you how powerful it could be. So the blue is just the score used for the level 1 trigger. And if you look at the orange one, these are seeded and plus the nominal from the number detection algorithms. And the red dash one is really the powerful one you should focus on, because this is the one that only triggered by the anomaly algorithm, but not the others. Therefore, we are able to trigger a large fraction of the new events that could be rejected if without our algorithms. And let me give another example about neuroscience. So neuroscience tries to understand the behavior and the brain activities. So for example, you could have a monkey to see the image of different pictures. Then you want to see if you can understand the brain wave activities and what kind of image that being seen by the monkey. So you have to do brain interface closed-loop development with the neural signal, decoding, control, and if you could try to stimulate your brain and see if you can complete this circle. So this is an innovation in University of Washington, one of our A3D3 members, and using these nanopixels, and this is the image of part of the sensor in the localized brain neurons, that when the activity happens, how you can actually visualize that. So currently, we have deployed a prototype of the hardware closed loop using an algorithm. This is LSTM-based algorithms, and we are able to let monkey to see an image or object, and we try to stimulate a laser light to see if we can control with the monkey behavior. The last topic is about how we can solve the problem of high throughput. So the coprocessor, typically, maybe what you have with your laptop right now is a pair CPU with a coprocessor. So if you need more computing power, and you just have much more device over here, but it's very expensive if you just do direct connect CPU to GPU device. So what we can do is we can use a few number of the GPU or servers to serve a large group of clients. And this way, we are able to achieve high performance computing with reduced resource. So this is more like how you use ChatGPT, right? You make a prompt to the server, and then the server return the result back to your client cell phone. So here, what we do is that we have deployed a gRPC protocol, and your client software can make a request to our cloud resource, and which collect the request of the AI inference calculations, then return result back to the client, then complete the full workflow. And we further upgrade to the supersonic, and this is also allowed to support multiple different type of the models. And also we have auto-scaling capability to highly optimize usage of the cloud resource. And here is one example in particle physics. And particle physics, the tracking is one of the critical problems. We are able to run the tracking algorithm using this workflow. And here's one plot showing the scaling performance. The GPU utilizations, the higher the better, and also the latency, the lower the better. So if you just use a typical connection of GPU compared to our supersonic, we are able to achieve high utilization with a low latency. And the other example from the gravitational wave detections, and this is primarily driven by the MIT team, and I'm very proud of being part of A3D3 and to mention this work. And here we talk about LIGO gravitational detections. If you want to really make it to be one of the early alert systems, and you want to identify this gravitational wave early and also broadcast to the world. So there are a couple steps you need to do. First, you want to clean the data, and then you would like to do event detection, detect those gravitational events. Then you want to categorize the data, allow you to localize where it is in the sky. Then you can broadcast to all different experiments in neutrino messenger or the photon messengers. So we have the contributor from our A3D3, the development of multiple package in order to accomplish each step. We use deep clean to clean the noise. And then we have event detections, and we can use A-frame, a CNN-based algorithm, and also the quark. This is also anomaly detection using semi-supervision method to detect the anomaly of the gravitational wave and without knowing the model. And then you can use the amplify to categorize the event and complete our full workflow. So we further generalize to multiple different domain science in different areas. And you probably can find one of your applications or one of your experiments the need in this 2D frame. Because the modern data analysis and also the big data science has been really moving to try to utilize more sensor multimodal approach, and also you want to make all this calculation in real time. So to promote our events, we have schools, workshops, and we have an upcoming conference in Zurich in September. And we also do an even bigger community building. It's called HDR Ecosystem Conference. It's also will be coming up very soon in Columbus. And we also do the International Machine Learning Challenge and Context. There's a FPGA design context, and also this is the Machine Learning Challenge, and the competition will be all the way to the end of December. We welcome everyone who is interested to broadcast this or even participate in this challenge. And this is Phil, like our co-director and deputy director, and we are trying to improve our communication so that more people know about the exciting work we have accomplished and share the tools that you can benefit from. And including the industry relations, we made quite a lot of effort to build this nice partnership effort. And we also train the next generation workforce, and we have a post-bac programs, and they accomplish amazing work that all together with the A3D3 members. And so we welcome everyone follow us. And if you know about undergrad or the first year of the student who just graduated, and they are interested about exploring their career, they can also check our post-bac program. So I share with you, we use HLS formula to solve the low latency problem, and we use supersonic to promote the client-server computing model for the high-performance computing for high-throughput solutions. And the ecosystem is continually growing, and we think this will continue to play a major role in the coming year of the AI paradigm. Thank you.
Thanks again for a wonderful talk. We take questions. Are there questions in the room? See anyone? Oh, yes.
Oh, yeah. I was just curious. Of course, with transformers now, Silicon Valley is chock full of startups that try to do like custom transformer ASICs for language model inference and so on. So, and they kind of promise like 500,000 tokens per second or millions of tokens per. So, do you have any sense how that work stacks up, kind of against these efforts that try to do basically accelerate language models?
So, we talk about. We can answer this in two different aspects. One is the edge device. So if you talk about how you would like to, for example, your cell phone or your FPGA with a limited hardware elements, you want to run large language model. That's with a transformer base. It's really limited by the resource. Therefore, the number of parameters you can use and the size of model is very limited. So, for example, currently, when we develop transformer for FPGA, what we achieve right now is that we can load up to 10,000 parameters to that. Right. So you could not run a typical sense of large language model on that.
Right.
And in that case, you could still use a large language model as your teacher model, and you need to train a student model, which is a much smaller scale. So you can still benefit from a large language model, but it's going to be a smaller model to run, right? But the second is that it's actually happening now. There are ASIC design specific for large language model, and there are several startup companies that are doing this approach.
Right.
And in that case, you are able to run bigger parameter models, but it's going to be tied to the particular structure they choose to design the chips. And these two are still very the hot and also quite top tier of the research directions.
Other questions? I have a follow-on.
Yes.
Actually, so one thing is maybe a bit more like broader perspective on different paradigms of doing AI.
Mm-hmm.
And do you think there are currently like alternative paradigms that are not essentially the classic transformers revolution that could benefit from FPGAs and kind of computation that one can do in boards like that? And are we not exploring it enough, or are there interesting directions in that sense that are these days like not very explored?
Okay, so let me rephrase, just try to be sure I can understand your question. So are you saying that other than are you asking other than transformer, are there other AI model can be benefit from loading on FPGA?
Right, yeah, are there alternative ways of doing, let's say, interesting AI that is not based on transformers that could benefit more than transformers or align better with computations on FPGAs?
Oh, okay, good. Okay, thank you for your question. All right. We actually, the answer is yes. Not every single problem you want to solve with transformer, because not every single question you want to solve with a large language model, right? In particular, the problems that we talk about here, for example, the autoencoder is one example. Autoencoder, you have the algorithm which try to see the signature difference between the control region data and the target of interest of data. In that case, a fully conditioned network with a couple layers and could already do a very good job. You don't need a transformer. Yeah. And also the image-based algorithms, and you feed in images for analysis. That is computer visions and using convolutional neural network with a couple of the filter and pooling layer, and then fully conditioned network follow. And that's also a much better usage, right? So we are not necessarily just tied to the transformer that can fit our goal. But the example I show here is we want to develop a generic toolkit that can apply to different type of data. Yeah. So I think the FPGA tool that we have developed here could support all different type of architectures and beyond the transformer. And we should also think about how to choose the right model as a good policy before we try to apply to solve our data problem, but not just using transformer as the only choice. Yeah. Okay.
Any other question? I have another one, little
yes,
one, very
please.
short. Actually, it's more interested about exploiting these technologies for mixture of experts. Have you ever developed anything based on FPGAs and boards that sort of exploits the idea of mixture of experts?
When you say mixture expert,
you mean like multiple algorithms running on multiple boards and use them as like modularly but combined?
Oh, I see your point. Yeah, this is actually already a design like we deploy in the particle field experiment, and every single sub-detector have their own trigger board, and each trigger board is built based on the FPGA. And I knew it's more than just particle physics, and also in a couple of astronomy that when you analyze CCD data, and it's a computer vision analysis, right? And you want to analyze data fast, you also use the FPGA. Yeah. And you combine those data from multiple FPGA output, and eventually you have a global master FPGA try to aggregate all those data and make the final global decisions. So this is already happening. Yeah, an easy example. Yeah, and I mentioned that we are doing international context on FPGA design. Whoever try to use the HLS format tool we mentioned here to deploy AI algorithms on FPGA board, and I seen a couple of the context results. They try to use multiple FPGA board to control different robots. And this is another example that you could combine multiple AI algorithm FPGA output to develop the creative applications. Yeah.
That sounds super exciting.
Yeah.
All right. Is there any more questions from the room? If we don't have any other question, we can.
Yeah, because I try to prepare my talk early. That's why we have more time for discussion. If there's no question from audience, maybe I can ask question to audience. Is that okay?
Yeah, sure. Yeah, we have more time. Yeah.
And because I'll try to control that. We can still finish it by 12:30, so we can go for lunch. Yeah.
That would be great. I mean,
Yeah.
if
So I mentioned about, I did not dive into the detail how we can run algorithm on FPGA, but there's one concept I want to share with everyone, because the AI model itself is big, but the hardware resource is limited, it's small, right? So the way we do it, we have to compress our model, and we have to quantize our model. Instead of 32 bits, we probably just use 8-bit, or even 4-bit data can achieve the performance or the error we are aiming for. If we have such an algorithm, right, can everyone think about, even though you are not working on the FPGA, you can still be benefit from this kind of algorithm. If you have a large language model or big neural network, do you see potential benefit for your own application? Like you can use our process of the compressed or quantized model to potentially speed up your calculations and be benefit from this. Yeah. So I just want to pitch this question to everyone to think about. If you see that, yeah, I'm not using FPGA, but if I can make my model smaller, and this will be super benefit for my own applications, please feel free to talk to me and also talk to Phil, and we'll be very happy to talk with you. Yeah. Yes, Lucas.
Yeah, I had a kind of related question to this. I mean, like machine learning is a great way to put things on a GPU because, like instead of writing CUDA, I just train basically like a neural network to approximate it, and then I can run it on the GPU. Great. So with the FPGA, I asked this question to a few people like Thea and so I never remember the answer. So like, can you create like a specific hardware that is like for a transformer, but where you can reconfigure the weights kind of on the fly, or is this always like a new design step? When you say, okay, if I manage to kind of translate every task that I could think of into a transformer, can I take the same chip and then like swap it out? Like for example, like update the trigger with some new like re-optimized transformer without somehow doing some complicated design step? So,
the short answer is yes.
Yeah?
Yes, and it's happening now. Right. Yeah.
Every time I ask the question, somebody says something different.
Yeah, because I think we cannot get away from large language model for a couple years, and that's really the building block is transformer, and this is why if we have a construction of the electronic element just as transformer as a baseline, and you can really easily configure that, you'll be basically in the next coming few years lead the technology trend for the actual deployment to the real calculations. Yeah. So in Seattle we met in some of the incubator accelerator startup events, and I knew at least 3 startup company. They try to design different approach for implement a transformer in the electronics.
We can also discuss over lunch or something.
Yeah.
I'm kind of thinking, okay, let's say you have like a transformer that like a 1,000,000 parameter transformer. And I give you 1,000,000 numbers and you run my algorithm. Like if I manage to kind of translate my algorithm into 1,000,000 numbers, can you kind of right away turn around and create an FPGA that does this? Or because I always think it has to go through quantization, and so it's not actually the 1,000,000 parameters, but then it goes through some kind of human engineering to figure out how to put it on the FPGA, and like the actual circuitry is different. And so I guess that's the question I'm asking.
Oh, so the FPGA one. FPGA is more changed, but because what I'm talking about is really specialized hardware. Yeah. We now have a prototype I call it prototype, although we support transformer, but it's true that we still require customization there when users try to use the tool. So because the variation, also possible adaptation to the transformer to different architecture is just such a large areas. So I think if you try to implement a really generic transformer FPGA block to support a connection to different network, you are designing a transformer that people might just use a portion of the code, but the other part they don't use at all. Maybe this is interesting question that for our engineers, like, is it possible to have a modularized transformer component and you pull the one you need, build it up? Yeah, but this process still probably need to recompile the code. Yeah, but not just a precompile. You can just load it. Yeah. So I answer this based on my knowledge about FPGA, but I think I don't know if this might not be the right forum to talk, but we should talk offline. Yeah.
All right, I guess we are right in time for lunch. So
yeah.
thanks again.
Okay.
Speaker.
All right. Thank you, everyone.